Now we're going to turn our attention to finding inverses of exponential functions. Find f inverse for each function. Give the domain, range, and asymptote for f and f inverse. Our first function f of x is equal to 6 to the x minus 1. I'll write down what I can. As far as f is concerned, the domain is, of course, all real numbers, because any number can be an exponent. The range is the set of positive numbers, 0 to infinity. And exponential curves have a horizontal asymptote of y equals 0 unless they've been transformed. To find the inverse, we're going to use the switch and solve technique, except it's going to be a little bit different. I'm going to write down x is equal to 6 to the y minus 1. Well, it's not different, just the concept is different. In this case, we have y in the exponent. And if you recall, a logarithm is an exponent. And so what we're looking at is, if I want to try to solve for y, then I'm going to use the inverse of an exponential. And so I'm going to write down the log of x is equal to y minus 1, because a logarithm is an exponent. But wait a minute, what's the base? The base was 6. And so this is log base 6 of x is equal to y minus 1, which means that y is equal to the log base 6 of x plus 1, and that is our f inverse. So f inverse of x is equal to log base 6 of x, and I'm going to put the x in parentheses to make it really clear that the 1 isn't part of the argument of the logarithm. Now I can finish this off by saying for f inverse, we have a domain that is the set of positive numbers, 0 to infinity, a range that is the set of all real numbers, and those are obtained, by the way, because the domain of f is all real numbers. The range of f is 0 to infinity. And then the horizontal asymptote for the function f becomes now a vertical asymptote for the inverse, and it's x equals 0. So that's all of the information that I was asked for, together with the inverse function. I don't know how clear that was, so we're going to do another one. F of x is equal to 2 to the 3x plus 1 minus 6. First, we're going to look at the domain, range, and asymptote for f. We have a domain of all real numbers, because that's true of exponential functions. We have a range that is going to be negative 6 to infinity, because if you think about what the negative 6 means, it's a vertical translation down of 6 units. So that's going to affect the range. It also affects the horizontal asymptote, which in this case is y equals negative 6. Using the switch and solve technique that we just used, we're going to write down x is equal to 2 to the 3y plus 1 minus 6. Now the variable that we're solving for, y, isn't an exponent. That means we're going to be using a log. First, I'm going to isolate the exponential term. So I'm going to add 6 to both sides. We get x plus 6 is equal to 2 to the 3y plus 1. And now I know that a logarithm is an exponent. So log is equal to 3y plus 1. Log of what? X plus 6. But now, what's the base? The base is 2. So now we have log base 2 of x plus 6 is equal to 3y plus 1. Continuing to solve for y, we get 3y is equal to log base 2 of x plus 6 minus 1. And notice again, in this case we have x plus 6 in parentheses, because I want to make it clear that that is what the log is holding. And then finally, dividing both sides by 3, we get y is equal to, we can say log base 2 of x plus 6 minus 1 all over 3. That would work for me. And so we would say let me just erase this, is f inverse. See, we were told to find f inverse, and so it's appropriate to give it an inverse function notation. Now for f inverse, I look at what I knew about f. I'm going to get the domain and the range by reversing those for the function f. The domain is going to be -6 to infinity. The range is going to be all real numbers. And the horizontal asymptote for the function becomes a vertical asymptote for the inverse, and that's x equals -6. Just a little note, the domain -6 to infinity is obtained by looking at the argument of the log x plus 6. We want numbers that are going to be positive in that argument. In any case, here we have our information for f and f inverse that was asked, as well as f inverse itself. Next, we're looking at f of x is equal to the natural log of x plus 4. This is a log, so we're finding the inverse of it, and that inverse is going to be an exponential function. I think I want to hold off on writing down the domain and range. First, we're going to find the inverse using the switch and solve technique. So x is equal to the natural log of y plus 4. Now I want to use the inverse. The inverse of a log is an exponential. That's a two-way street. And so I want to write that the logarithm, ln, is equal to x, which means the x is the exponent. I need something with an exponent of x, but what's the base? Because it's the natural log, the base is e. So e to the x is going to equal y plus 4. I know this is all weird, but let's try to process what you can. And as you watch more videos throughout this topic, things will hopefully fall into place a little more. In any case, now I'm solving for y, and so e to the x minus 4 is equal to y. And so I'm going to write down that f inverse of x, right, showing good form, is equal to e to the x minus 4. Now we can look at the information that's being asked for f and f inverse. I'm going to look at the inverse function. The domain of the inverse is all real numbers, because that's true of all exponential functions. The range is considered by looking at the minus 4, which would be a vertical translation down 4 units. So the range is going to be -4 to infinity, giving us a horizontal asymptote of y equals -4. Whether you did that or not, we could look at the argument of the original function, which was f of x equals natural log of x plus 4, to consider the domain. The domain of f is the numbers that don't give a negative argument, so -4 to infinity. The range of f is going to be all real numbers, and the vertical asymptote is going to be x equals -4. So that's the information that was asked for. Finally, we have f of x is equal to 2 minus the log base 3 of x plus 1. And this one I'll do a little bit differently than we did the last. We're going to start with the domain. The domain is going to be the set of numbers that don't make the argument negative. That argument being x plus 1 means the domain is -1 to infinity. The range, because this is a logarithmic function, is going to be all real numbers, and we have a vertical asymptote that's related to the domain of x equals -1. Now, using the switch and solve technique, we're going to write down x is equal to 2 minus log base 3 of y plus 1. Again, it's weird. It's weird, I'll grant you. First, we're going to isolate the logarithmic term. So I have that x minus 2 is equal to negative log base 3 of y plus 1. And now I have this negative in front of the log term because it was 2 minus the log. A lot of people lose that negative, by the way. So I'm going to multiply both sides by -1. that's going to have the effect of making it so that on the left-hand side, x minus 2 becomes 2 minus x, right? They both change signs, and then I rearrange the order. That's equal to log base 3 of y plus 1. Keeping in mind now that a logarithm is an exponent. The exponent is going to be 2 minus x. What's the base? The base is 3. So 3 to the 2 minus x is equal to y plus 1. That gives me finally that y is equal to 3 to the 2 minus x minus 1. And then showing good form, I'm going to rewrite y as f inverse of x. So that's the inverse, and then the information that we were asked for the inverse. The domain is going to be all real numbers. The range is going to be -1 to infinity, and we have a horizontal asymptote of y equals -1. Now that we've thoroughly explored the inverse nature of logarithms, see if we can evaluate some logarithmic expressions. Log base 5 of 25. Remember what this is asking. It's asking for the exponent. What is the exponent on the base 5 that gives me 25? Answer is 2. Again, the reason is that 5 squared is what's equal to 25. Log base 3 of 81. What is the exponent on 3 that gives 81? The answer is 4. So log base 3 of 81 is 4 because 3 to the 4th power is 81. Next we've got log base 81 is equal to 3. What? So I'm looking for an exponent on 81 that gives me a result of 3? Well, since 3 is the 4th root of 81, we're looking at log base 81 of 3 is 1/4. Right? So we're going to use fractions to indicate radicals. And so log base 81 of 3 is 1/4 because 81 to the 1/4 power is equal to 3. Next we have something a little more abstract, log base b of 1. So the base is b. We're looking for the exponent because a logarithm is an exponent. That gives me 1. And so b to the something is equal to 1. Remember, 0 is an exponent that gives me 1. And so log base b of 1 is 0 because b to the 0 is 1 for any base other than 0. Next, log base a of 0. Remember, bases are positive, and so we're looking for a number that we put as an exponent on a that gives me 0. That's actually not going to happen. It does not exist, so I'm writing DNE. No logarithm or exponent on a positive base is going to give you a 0. And you recall the domain of a logarithmic function does not include 0, and so that was just to make sure that you're paying attention. Next we're going to look at an application of logarithmic functions. The pH of a solution actually has a logarithmic definition. It's defined to be pH is equal to negative log of H plus in brackets. The H plus in brackets is the concentration of the hydrogen ion, and the units are molarity, which are denoted by an uppercase M. You want to know more about this? Take a chemistry class or ask me in class. I want to note two things. Number one, log of H plus, what's the base? The base is 10. And number two, pH, it's lowercase p, uppercase H. That's not a mistake. The H actually refers, it's the chemical symbol for hydrogen. And the P, check it out, when they figured out the pH stuff, they knew that a logarithm is an exponent. And so P is actually the power. It refers to an exponent. Not like the strength power, but power as an exponent. You need to know, like, basically none of that for right now. What you need to know is that we are asked to find the pH of stomach acid if the hydrogen ion concentration is 0.0316 molarity. Here's the deal. I have this number, 0.0316. It is represented in H plus in brackets. That H plus in brackets is in the formula. Hence, pH is equal to the negative log of 0.0316. Putting that in my calculator gives me that pH is 1.5-ish. With pH, two things. Number one, we don't use approximately. We don't use squiggly equals. Number two, pH is generally given with 1 decimal place. And so here we're going to say that pH is 1.5. That's what's going on in your stomach. As far as the pH scale is concerned, it goes from 0 to 14, with 7 in the middle being neutral. Anything with a pH that's between 0 and 7 is acidic. It's an acid. Anything with a pH to the right of 7, that's between 7 and 14, is a base, or they also say alkali or alkaline. So our stomach acid, being a pH of 1.5, is acidic. Next, we're asked to find H plus in brackets, the concentration of the hydrogen ion of seawater if the pH is 8.2, which, by the way, makes it a base, basic. I, again, don't need the chemistry lesson. I need to know that there exists this formula that says that pH is equal to the negative log of the hydrogen ion concentration. And in this case, the pH is given to be 8.2, and so I can substitute that in place of pH. So I have 8.2 is equal to the negative log of the hydrogen ion concentration. Solving for the hydrogen ion concentration, we can say we can multiply both sides by negative, so negative 8.2 is equal to the log of the H plus. And now, what's the base? The base is 10, because it's just log. Keeping in mind that a logarithm is an exponent. I'm going to put down 10 to the negative 8.2, right? Make that negative 8.2 the exponent on 10, and that equals the H plus. I can put that into my calculator, which tells me that the hydrogen ion concentration is equal to, actually I'm going to squiggly equal this one, 6.3 times 10 to the negative 9. Really, really small number. If we scroll back up a little bit, we can see that it was given in molarity, which is denoted with an uppercase M. And so H plus concentration is equal to 6.3 times 10 to the negative 9 molarity. Again, take a chemistry class. Next, and finally, the sound level in decibels of a noise is given by a formula that also involves a logarithm. Decibels is equal to 10 times the log of I divided by I sub 0. That's weird. Where I is the intensity in watts per square meter, and I sub 0 is in particular 10 to the negative 12 watts per square meter, and that's the smallest intensity detectable by the human ear. Dude, what? Okay, there's a formula. Here it is. You don't need to memorize it. I want you to know how to use it. A couple of things. The decibels, lowercase d, uppercase b. That's a little weird. As a prefix, deci is related to 10, kind of like centa is related to 100. So there you go, deci. And then the B that's uppercase is actually in honor of Alexander Graham Bell. Yeah, who knew? So the decibels is indicating that there's a 10 and respecting Bell. But the formula is 10 times log. Log is an exponent of something, a ratio of I to I sub 0. I don't have to thoroughly understand all that to know that I can find the decibel level if I'm given a particular piece of information. And in part A here, we're asked for the decibel level of a normal conversation. being told that I is equal to 10 to the negative 7 watts per square meter, or 10 to the negative 7 of a watt per square meter. So the decibel level is equal to 10 times the log of 10 to the negative 7, that's I, divided by I sub 0, which is a constant. It's always 10 to the negative 12. Well, that becomes that the decibel is equal to 10 times the log of, using our exponents, we're going to end up with 10 to the 5th. And so what we'll find here is that the decibel level is, if we put that into your calculator, 50. So normal conversation, decibel level of 50. The threshold of pain, the I is equal to 10 squared watts per square meter. And so that goes into the formula. Decibels is equal to 10 times the log of 10 squared divided by 10 to the negative 12. Again, that negative 12, or 10 to the negative 12 is a constant. And so that's going to give me that the decibel level is equal to 10 times the log of 10 to the 14th. And if you either reason your way through that or put it in your calculator, you're going to find out that the decibel level is 140. Oh, I forgot to put the units, decibels. So 140 decibels, you're experiencing pain. Next, we're asked to kind of turn that formula inside out. We're asked to find the intensity of a whisper, which is given to be 30 decibels. Remember, we have that formula. It says that the decibel level is equal to 10 times the log of I divided by I sub 0, which is that constant, 10 to the negative 12. So for a decibel level of 30 decibels, I'm going to replace the decibel part with 30. So 30 is equal to 10 times the log of I divided by that 10 to the negative 12. Now, first, I'm going to divide both sides by 10 to get the log portion all by itself. And that's going to give me 3 is equal to the log of I divided by 10 to the negative 12. Now we're looking at a logarithm is an exponent. The base is 10, and so we're looking at 10 to the third is equal to I divided by 10 to the negative 12. That's going to give us that I is equal to 10 to the negative 9 of a watt per square meter. And if you want to know what that means, take, I don't know, maybe a physics class. Last, the front row of a rock concert is given to be 120 decibels, which you may note is pretty darn close to the threshold of pain. So we're going to put 120 in place of the decibel portion. That's equal to 10 times the log of I divided by 10 to the negative 12. It's the same process that we just went through. And so 12 is equal to the log of I divided by 10 to the negative 12. The base is 10. A logarithm is an exponent. And so we have 12 is the exponent on the base 10, and that's equal to I divided by 10 to the negative 12. And that gives us that the intensity is equal to 1 watt per square meter.